first thing we're going to start with is coterminal angles, and we've actually one thing that we had to do with 9 pi over 4 is we had to subtract away the 2 pi because it ended up being more than 1 full revolution. That's an example of a coterminal angle. And so basically when we're describing coterminal angles, we're describing 2 angles and possibly different rotations, okay, called coterminal angles. An example of this is just like if you look at a clock, right? Like this, let's use the second hand or the mint hand, for example, right? The 12, that we would call that being the same location where it has the same terminal initial sides, but different revolutions to get to that point. And so what we're going to do is we're going to subtract away and
Isn't this the same as modulus?
I don't know.
Because modulus gives remainder of something divided by something.
I don't think so. I don't think so. No, can you shut that door for me? Subtract 360 or add 2 pi or subtract 2 pi. So the work for it isn't all that difficult. Everyone good here? In coterminal angles, we're going to describe an angle that is positive, so meaning greater than 0 and less than 360 degrees. And so most of the time, again, we're just adding or subtracting 360 with degrees. Now, degrees, if I want to find an angle that is coterminal with 420 degrees, I'm going to subtract away the 1 full revolution. So minus 360 and get to 60 degrees. And so we would describe and this is what we saw on Friday. And that if I were to draw this angle at 420 degrees, it'd get us to this position at 60, but when we draw it, both of them have the exact same location, just different rotations to get to that position. All right, so now with B, that is a negative. Just know that you do not need to draw the angles to describe the coterminal angle. This is just kind of me adding in the explanation of what coterminal is. And so this negative 120, remember negative (180), and so negative 120 is 30 more degrees in the negative direction than 90. Okay, so this right here is negative 120. And so if I angle that is positive and less than 360. So we're going to do something different. This time, we're going to actually add a full revolution. So add 360 from this position, and that gets us but now it's going to end up being positive. So in the green, that's me showing us adding that full revolution to get to the same position. And so instead of subtracting, we're going to add 360, getting us to 240 degrees. So 240 is coterminal with negative 120. Sarah, do you have a question?
It was just that, so when it's negative, even on the chart, you have to switch the 270 and the 90. Right?
Yeah, well, so, okay,
Like,
so.
you have to write that. I'm so.
Yeah, I got you. The sign of the angle tells us the direction which we rotate. So when it's positive, we're rotating counterclockwise, and that's why this would be labeled as 90, because a quarter turn is 90 degrees.
Yeah.
Regardless of the direction, half a rotation is 180, 3/4 is 270, and the full rotation is 360. Now when I make it negative, we're changing the direction. So a quarter turn is still 90 degrees, but now since it's the opposite direction, it's negative 90, okay, in that quarter rotation direction. And so then negative 90, negative 180, negative 270,
Okay, that makes
and then negative 360 all the way around, okay? So it's more about the direction in which we rotate. Go ahead.
So can you draw the rotation?
Let's have you all find the coterminal angles here, but with the radians as opposed to the degrees. And you're going to have to work with the fractions here and add, subtract 2 pi. Okay, so let's you all practice that. I'm going to go over it, give you a couple minutes to do so. I'm going to go over it. Okay.
That is not right. Tommy says it's not right.
Common denominator, the fraction work is not going to go away. I've had some people that have been wanting to convert to degrees, which you can convert to degrees, but then you're going to have to convert it back to radians at the end, so it ends up being more work. And we can't shy away from the fractions and can't shy away from the radians. Okay, if you do that, it's just going to make the rest of the work we do with radians and degrees really difficult. So don't convert to degrees, okay? It's basically what I'm saying, okay? Try to just push yourself to work with the fractions and the radians. So to get a common denominator, multiplying by 6 over 6, that makes 2 pi 12 pi over 6. And then when I subtract these away, 17 pi minus 12 pi, that's the exact same thing as doing like 17x minus 12x, which is 5x. But x in this case is the pi, right? So they're like terms. So I can do 17 pi minus 12 pi and call it 5 pi. So 5 pi over 6 is coterminal with 17 pi over 6.
So, you did not want us to convert to degrees on this?
No. No. If you did, it's okay. But again, we want to stay within, if we're working with radians, leave it in radians. If it's in degrees, leave it in degrees. All right, then in part B, negative pi over 12 plus 2 pi, so getting a common denominator of 12 over 12. So 2 pi is 24 pi over 12. And I subtract away 1 pi, it gets me to 23 pi over 12. Okay, simple enough, right? Just adding, subtracting. Yeah, Libby? Add 12 pi over pi. So, again, there can be more than one revolution, right? Talking about my example with the clock, right? That minute hand is going to be at 12 multiple times throughout the day, accounting for multiple revolutions. And so what we're going to do with the next ones is we might have to subtract away more than one revolution to find the coterminal angle.
So why is...
Is to do the same thing, find an angle that is between 0 and 360 and coterminal to the given angles here. And some of you are going to notice 750, well, that's not even just one rotation, but that's 2 rotations, right? So a quick way to get the coterminal angle here would be to subtract away 720 degrees, which is 2 revolutions, end up getting 30 degrees. Okay, but some of us may not see that right away. And so we can go about it the exact same process of what we did before, where we can just subtract away 1 revolution at a time. And so if I go 750 and minus the 1 revolution, which is 360, I get 390. And 390 is still greater than 360. So we're still more than 1 full revolution with this angle amount. So I'm going to have to subtract away another revolution. So 390 minus 360 is 30 degrees. And so 30 degrees is coterminal with 750, which is also coterminal with 390. Yeah? Okay, so like I said, some of you will just automatically know, like, hey, I got to subtract away 2 revolutions. 2 revolutions being equal to 720, and you can do that all in one step. It's not as obvious as we work with radians because of the fractions. So here, 22 pi over 3, well, if I just think about the 22 divided by 3, that's like 7 1/3. So we basically have 7 1/3 pi radians here. So we're going to have to subtract away not only 2 revolutions, but more than likely a 3rd revolution. Now again, I don't know that many of us are going to see that right off the bat with these being fractions, because we still need some work with those fractions. So let's just go about it the same way. 22 pi over 3 and subtract away 1 full revolution, which I'm just going to get the common denominator right here. I'm not going to show that step. 2 pi in terms of thirds is 6 pi over 3. So this is that 1 revolution equal to 2 pi. So when I subtract this away, I get 16 pi over 3, which is still more than 2 pi. 3 goes into 16 5 times, so we're like 5 1/3 pi. So we're going to have to do it again. So 16 pi over 3 minus another 6 pi over 3. This is 1 full rev, which is 10 pi over 3. 10 pi over 3 is still more than 2 pi. Right, that's about 3 1/3 pi. So we're going to have to do it one last time and subtract away 6 pi over 3 again, which is 1 full revolution, getting me to 4 pi over 3. So 4 pi over 3 is coterminal with 22 pi over 3, which is also coterminal with 16 pi over 3 and 10 pi over 3. After we subtract away all those revolutions. So with the positive radian measure, it's a little bit tricky because right at each point I had to ask myself, okay, am I still greater than 2 pi? Right, I had to do a little bit of fraction work to decide that 16 over 3 is still more than 2 pi, and that 10 over 3 is still more than 2 pi. So it's a little bit trickier when we're subtracting away the radians. When the radian starts as negative though, and we're going to add the 2 pi, it's a little bit more obvious because as soon as it ends up being positive, we're done, right? So with the negative 17 pi over 3 or over 6, we're going to add 2 pi this time. And again, in sixth, 2 pi is equal to 12 pi over 6. And that's that 1 full revolution. And so when I add it the first time, I get negative 5 pi over 6, which is still negative, telling me that I need to add another revolution again. So negative 5 pi over 6 plus another 2 pi, which is 12 pi over 6. Again, that's 1 full rev, is 7 pi, should be a 6. 7 pi over 6. So 7 pi over 6 is coterminal with negative 17 pi over 6. Yeah, question?
Is there a way?
Is finding the length of a circle or an arc, okay, the circular arc of a circle. So the length of arc length, sorry. I don't know why I'm struggling there. The first thing I want us to know is this equation we have seen already, okay, just in a different form. We've seen this diagram already. So one thing that you have in your notes, that an angle measured in radians is equal to the arc length S divided by the radius R. This was essentially the definition of radians. Definition of radians. And again, that's already in your notes. That's something we put in on Thursday of last week. And the reason I bring this up, because if I wanted to find the arc length, that arc length is derived from this equation, right? If I take theta equals S over R, and I multiply both sides by R, we get S by itself. And so the arc length is equal to the radius times the radian measure. And I want us working on making those connections. And one thing I talked about last week is trying to make more connections and think about math more conceptually as opposed to just memorizing steps. There's going to be a lot of steps within this whole unit. And if you're just trying to memorize all the steps, it ends up being too much. And I think that's part of what some of you try to do with the log test. That's why it didn't quite go as well as maybe you would have liked, because there's a lot of steps there. We want to be more conceptual as opposed to just memorizing steps. Okay? And this is what I mean by that. Making those connections that you're like, hey, this kind of looks familiar. Right? It's familiar because we've seen this equation from the definition of radians. So when we want to find the arc length, if we know the radius of the circle of that arc, and we know that the angle measure created by the central angle, we can just multiply the radius times the angle, but the angle, theta, needs to be in radians. And the reason it needs to be in radians is because of this equation for arc length being derived from the definition of the radian. So this says we have a radius of 10 inches. Okay, so you can kind of, if you want to make this circle and have a diagram for it, you can. R is 10. We need to find the length of the arc intercepted by a central angle of 120 degrees. So this angle would be 120. That's how much we've rotated from the initial side to the terminal side. And so the first thing that I'm recognizing is this angle was measured in degrees. Well, for the arc length, we need the angle measure to be in radians. So I'm first going to take this 120 degrees and convert it over. From here on out, anytime I convert between degrees and radians, I'm going to just do the shorter way rather than setting up the ratios. But again, remember the ratios work every single time if you ever forget. And so the quicker way is to take 120 degrees and multiply it by, and this is what a lot of you might run into if you try to take the shortcut. You're like, I know it's either pi over 180 or 180 over pi. And so we just need to think about, okay, which one does it need to be here? Well, since I'm going to radians, every radian that we write has a pi in the numerator, right? If you look at any radians you have on your paper, the pi is always in that numerator. And so making that connection, I'm like, okay, I got to multiply it by pi over 180. So then this is 120 divided by 180, which I'm going to let the calculator reduce that down for me. So quick reminder that to reduce it down, you do the division. 120 divided by 180, press math, and then enter, and it'll make that conversion for you. So 2/3, or 2 pi over 3. Now that we have the angle measured in radians, the arc length is equal to that radius of 10 inches times the radian measure of 2 pi over 3, which is equal to 20 pi over 3. And since this is something that we can measure, let's go ahead and give like an approximate value by doing the 20 pi divided by 3, which is 20.9 inches. It would be the approximate length of that arc. All right. Questions here? Okay, we're almost done. Last thing are a couple applications. Measuring speed. And so to kind of set this up, know that there's different ways of how we can interpret speed. And I think this kind of top paragraph here does a good job explaining this. So it says, a carousel contains 4 circular rows of animals. As the carousel revolves, the animals in the outer row travel a greater distance per unit of time than those in the inner rows. So what this is describing is, let's just make like a quick sketch of a carousel. Right, we have the inner circle of animals, which I'm just going to draw as squares. I'm not going to draw an actual animal. And then there's another row of animals a little bit further out. And we'd have 2 more rows. I'm not going to add those 2 more rows. Okay, but as this thing rotates, right? All these rows of animals are connected to like an axle that just rotates around, and they complete one revolution in the same amount of time altogether. Okay, but what's different is the rows in the outer, or the animals in the outer row, they have to go a greater distance in the same amount of time as the inner rows. And thus, the outer row of animals have a higher linear speed being just how we think of speed in general, distance divided by time. Okay, and that's what this is saying here. Okay, the outer row travel a greater distance per unit of time than those in the inner rows. Thus, these animals have a greater linear speed than those in the inner rows. Okay, but by contrast, all animals, regardless of the row, complete the same number of revolutions, so one full rotation, per the same unit of time. And thus, all animals in the 4 circular rows travel at the same angular speed. So there's multiple ways of how we can interpret speed. Okay, think about angular being measured in terms of rotations, and linear being just what we already know about speed, distance divided by time. Right? So multiple ways to think about that speed there. Bringing us to 2 equations, starting with the linear speed, represented by the variable v. So this is that linear speed. And just in general, linear speed is, and this is relating to circular motion, so s being the arc length, which is essentially the distance divided by time t. And then the angular speed represented by the variable, that is omega, that W-looking shape, the Greek letter omega. And again, I'm not going to quiz you on your knowledge of Greek letters. Don't feel like you need to memorize those. Okay, but when you see that omega, it's referring to the angular speed, which is equal to theta, which is the rotation, measured in radians per unit of time. The time itself, or the unit of time, does not matter. It can be minutes, seconds, hours, days. The rotation has to be measured in radians, though. That part's really important. Now, if we combine these 2 equations together, it comes up with another form of linear speed, or another way to find that linear speed, if we're dealing with rotations here. And so down here is just one more form of this for the linear speed. Again, that's represented by the variable v being equal to the radius times the angular speed. This equation is derived from both of these being combined together. And so we easily could manipulate these equations and substitute variables in this equation up here to come up with this new linear speed equation. But we're not going to do that in here. We're getting to the point where there's a lot of equations and a lot of formulas. As we progress through the week, you're going to see there's a ton more coming. Know that most assessments, I'm going to provide almost all of the equations and formulas for you. There's, I don't want to say very few, but you don't need to memorize every single one. And I'll point out the ones that you do need to memorize as we kind of work through this unit. Okay, but there's going to be a lot. Okay, so I'm going to work through just one application dealing with this linear speed and angular speed, and then have you all try one on your own. And that'll bring us about right to the end of class. Know that there is a Math Excel assignment for this lesson. It is due Tuesday night at midnight. Most of the, I shouldn't say most, but a good portion of the questions are just those coterminal angles. So none of the work should be super time consuming. All right. A wind machine used to generate electricity, same kind of wind machine that we have not too far from school here, that has blades that are 10 feet in length. Always a good idea to underline and identify any mathy words or mathy parts that we might need. The propeller is rotating at 4 revolutions per second, okay, which is pretty fast. It says find the linear speed in feet per second of all the tips of the blades. One thing that we did first semester with these word problems that I think can be really helpful for those of us that struggle is identify what we're given and what we need to find. And so when I read this problem, I know that I'm given a length of these blades, and as they rotate, that ends up being the radius. So the radius of these blades as they rotate is 10 feet. Then I'm given something about 4 revolutions per second. Well, that is angular speed. Okay, so W being the angular speed, which is equal to 4 revolutions per 1 second. Again, the unit of time does not matter, but we need this omega. It needs to be in radians. So we're going to have to do some unit conversions to make that happen. So I'm like, okay, I know I have R, I know I have omega, or the angular speed. We need to find V, which is the linear speed. And one equation that we have for the linear speed is that radius times the angular speed omega. And we're given both of these variables, right? R and omega. The only thing that we need to do with this angular speed omega is that unit conversion. So we're going to do that first. We're going to take these 4 revolutions per second. And this is the same kind of unit conversion that you would do in a science class. So hopefully this isn't new for any of us. Even if it is, it's okay. We'll go over it right now. And so when I'm doing this conversion, I'm like, okay, what unit needs to change? The seconds don't need to change, right? We can leave this in feet per second. What needs to change is these revolutions, right? The revolutions need to end up in radians somehow. So when I want the revolutions to go away, or any unit to go away, if that unit shows up in the numerator, it needs to also show up in the denominator, so that way it divides out. So I'm like, okay, what do I know about revolutions? I know that 1 revolution is equal to 2 pi radians. And by making that conversion, the revolutions divide out, leaving us with radians per second. So this ends up being 8 pi radians per 1 second. Which then allows me to use this equation to find the linear speed. So linear speed V is equal to the radius of 10 times the angular speed of 8 pi, which is 80 pi. And then we're just going to go ahead and come up with a value for that. That is going to be rounded slightly. So 80 pi is 251.3. And the units being seconds in time, feet per second. So that's going to be the one choice we're going to have to make. And biggest thing we need to think about is what are our ending units here? All right. Questions here. Leo, you had your hand up? Were you just trying to help me out with the unit conversion? Okay. All right, I do want us to try one of these problems on your own. So in our last little bit of class, I'm going to have you figure this out. Long before iPods that hold thousands of songs and play them with superb audio quality, individual songs were delivered on 75 RPM and 45 RPM circular records. A 45 RPM record has an angular speed of 45 revolutions per minute. You need to find the linear speed in inches per minute at the point where the needle is 1.5 inches from the record's center. Identify what you're given, what you need to find, and see if you can't come up with the linear speed for this problem.